quantization, but in more great format, and it was on the conference lecture. Well, let we have classical dynamical value A from QP. QP canonical variables from classical phase space. By the definition, quantization called linear if operators which corresponds to the symbols Q A Q P A P have a symbols which can be expressed by the linear operation over the symbol A. For example, classical symbol A corresponds to the quantum operator A, here classical phase space, and here Gilbert functional space. And that, for example, classical symbol QA corresponds to quantum operator B. So this symbol and this operator can be constructed from the operator A, or somewhat, well, by such a manner. Alpha Q plus beta P plus gamma D over dQ plus delta D over dP A. Sorry. Classical symbol which corresponds to the quantum operator QA defines by 4 arbitrary parameters: alpha, beta, gamma, delta. And if we have 16 parameters, then we completely define the linear quantization of the polynomial algebra. This is a definition of the linear quantization. For linear quantization, we can this general definition transform to the more convenient expression by the kernel of the linear transformation of the classical symbol A to the matrix element of the operator. Let A tilde xy is a kernel of quantum operator A. That is, for each vector from Hilbert space, A psi is defined as integral maybe as a generalized function A, then there exists such a kernel, which called kernel of quantization, K, Q, P, X, Y, such as A at X, Y is equal to classical symbol and kernel of quantization, okay. X, Y, dq, dp. For the sake of simplicity, I put n equals to unit for one-dimensional case we shall consider. The main kernel defined by following formula. Kernel corresponds to so-called tau quantization. K sub tau is defined as 1 over 2 pi delta q minus tau x minus 1 minus tau y x y. Yeah. For example, if we have a classical value q, its ordinary coordinate what is the operator of this classical symbol? Matrix of this operator q from xy is defined as q sub tau for this kernel, k tau dq dp. Well, after integration of the p over p, we obtain delta function of x minus y. Yeah? And by the integration of the q, we obtain q equals tau x plus 1 minus tau y. Then we have the follows. After integration over q, we obtain this value, and after integration over the p, we obtain delta x minus y tau x plus 1 minus tau y. Obviously, it is equal to, because x equals to y, y times delta x minus y. This is obvious result that matrix element of classical coordinate Q is delta function, and this representation of coordinates in Hilbert space. For impulse, in analogously manner, we obtain the derivative of the delta function and I. In general case, if we have a classical symbol in the form some function of Q times P in the m power, then by this method we obtain the following operator kernel. F of tau x plus 1 minus tau y PM Yes. Well, and minus I. Yes, minus I. Well, this expression doesn't depend on P, so so this is equal to tau x plus 1 minus tau y out now minus eliminated, and delta m over x minus y. Oh no, minus is not eliminated. Okay. Well, if we act by this kernel over function from Hilbert space, we obtain a sub tau. It is equal to the following expression. Well, it is equal to sum over k from 0 to m think d m minus k over d x minus k C x. Well, and 1 minus tau, 1 minus tau, k, c. Yes. 1 minus tau obtained from the differentiation of the f over y k times. Yeah. Well, if we want that A is observable, then corresponding operator must be Hermitian. Theorem: for linear quantization with linear kernel, operator A is Hermitian if and only if so-called symmetrization function is a function symmetrical with respect to 1/2. Namely, let k, q, p, x, y is a linear combination of the tau quantization. With some symmetrization function q big with tau, k tau, q pi, x, y. With the condition of norm tau equals to unit. Theorem: q tau equals q 1 minus tau. Is it obvious condition for students? No.
At least for me.
Okay. Let's go. If A is Hermitian operator, then complex conjugated and exchange y is the same operator. We have Hermitian conjugated defined as follows, and let this operator is the same. Well, for this, obligatory obtain k, q, p, x, y equals k, q, p, y, x. If is it so, then we obtain this condition. Okay. Let's consider for this formula we use this definition. If we change x and y, we use this condition, then after integration over dt, we obtain the same result. Now change xy and complex conjugated. Оп, оп, оп. Все то же самое. It's the same. And here and here. But tau and minus tau we can change here, yes, and transform it to the previous form. Okay. Hermitian quantization can be expressed in terms of moments of this distribution function. It is not really distribution function because the condition of normalized for the function q doesn't suppose that q is positive. Q is an arbitrary function with this condition. So it is differ from classical probability scheme, but in general we have statistical mix of this partial tau quantization for linear quantization in general. Well, if we have the kernel for this case, we must integrate this value with the use of this condition over tau. If this condition is valid, then we obtain the following form. From 0 to m, ckm is e power m k x sigma k the m minus k over the x m minus k, where sigma k is defined as a moment of the distribution function, quasi-distribution function q. It is easy to show that if this is valid, then sigma 1 is equal to 1/2. Integral q at tau, the tau is equal to unit. This is the first term, and it is equal to 2 times tau q tau the tau. It is obvious transformation, yeah? Then this integral is equal to 1/2. All Hermitian quantization have the first moment of symmetrization function equals to 1/2. The second moment is arbitrary, absolutely arbitrary function, sigma 2. Sigma sub 3 expressed from this and this moments. Sigma sub 4 is an arbitrary value. Sigma 5, in accordance with this representation, 1 minus tau k 1 tau is equal to tau k quad t d tau. We can expand this and express sigma k or the sigma of the previous numbers. So if we have the full number of moments of quantization function, we have this function according to Karleman theorem, for example, when the distribution function is defined by its momentum because such an integral is a characterized function of the quantization is equal to the power series sum from k at infinity k sigma k. Okay. So if we have sigma k, we know symmetrization function continuously. If q over tau is equal to delta function of tau minus 1/2, we have so-called Weil quantization. Q tau is equal to delta tau minus 1/2. So the kernel is equal to, in this case, q minus x plus y over 2. Sigma k is equal 1 and 2 k powers. The quantization when all operators p stand from the right part and all operators q stand from the left part, called p quantization. And if all operators q stand on the right part, this quantization is called q quantization. Corresponding symmetrization function defined as q tau equals delta tau minus 1 at tau equals delta at tau. These quantization are not Hermitian, but quantization by Jordan equal with the kernel 1/2 delta tau minus 1 plus delta tau is Hermitian. What's the main problem in this technical mathematical exercises? The main problem is that if I have to calculate the average value of dynamical operator, then I need to construct so-called density matrix and calculate the trace of this matrix with operator A. But there is another way in these terms. We can write the integral Rho is a linear operator with unit trace, positive linear operator in Hilbert space. And if rho xy and a xy is corresponding kernels, then this is equivalent to the integral for this kernel. We have an expression from the quantization kernel. Well, and now let's integrate first over dx dy. We obtain the following. We obtain the integral over the classical phase space nqp times some function which is called Wigner function, where this function, as it is evidence from this, is defined as well. This is a quantum operator. This. And if we have only tau quantization, we can bijection between W and rho. And if we have the total quantization with this symmetrization function, the inverse transformation cannot be obtained in general. Only wave quantization gives the inverse formula. We can explicit form if we substitute for this expression k sub tau. this. So it is obvious that operation of symmetrization is linear and for Wigner function. Then W where Q P is equal to W sub tau Q P Q tau d tau, where W sub tau obtained from this formula where K is K sub tau. W sub tau. QP equals 2. Well, we can simplify this expression if we introduce the variable z equals x minus y. Then here argument is equal to q minus tau times z minus x. Yeah. Plus. Well, and then we obtain the follows. Ok. And over x, I already integrated. It is equal to plus tau z tau z tau z pi z dz. Yeah. And only if tau is equal to 1/2, we construct the total Wigner function from the density matrix and inversely. So we have that if we want to derive the evolution equation of the average values of quantum operators or evolution equation of density matrix, then in terms of Wigner equation, we obtain the quantum operator with displacement of the arguments. Equation for density matrix. For Hamiltonian system is local over the coordinates, and equation for Wigner function is non-local over the coordinates. But Wigner function enables to obtain the expression formally in classical phase space. So Wigner function is very useful for some problem connecting with the classical approximation. And also in quantum optics for coherent states, this function also very often is in use. Well, we obtained now the evolution equation for W. It's the main aim of my lecture.
For a fixed Hamiltonian?
For an arbitrary Hamiltonian. If the Hamiltonian has the separated variables, it is very simple. But if we have an arbitrary differential function, classical function Q P, from this definition, which I give, we can construct evolution equation for W from this. So this is very monstrous technical operation, but in fact it connects with Fourier transformation, not all, but this transformation and displacement are very monstrous expression. So I want to write this equation and discuss about it without detailed technical expression. First of all, we write the evolution equation for Wigner function corresponding to partial tau quantization. Piece of paper. This equation is very difficult and long. Well, W sub tau is defined as S. Okay? Here, Fourier transform or the Hamiltonian. Times characteristic function of quantization in vector case, here a scalar product. Exponent times I e q plus omega pi plus minus tau k omega times w tau q minus tau omega p plus 1 minus tau k minus w sub tau q plus 1 minus tau omega p minus tau k. K d omega. This is a final equation for Wigner function. Maybe it depends on t. When t and the main problem is that if we want to construct the evolution equation for the total Wigner function w, when is linear combination of partial Wigner functions, then evolution equation for this function cannot be expressed from the some finite difference operator for this function. Only for the partial quantization. And it means that in practice we can maybe we can obtain the quantization for this concrete Hamiltonian and measure the corresponding momentum of the symmetrization function. If we observe the evolution of function w, this function. This function is not observable, but the corresponding Fourier transform of w is observable, as we know from Vladimir Ivanovich Manько. And here I think that this general consideration of the object that is not correctly defined with respect to point observation. This is this displacement and this displacement, if we introduce a Planck constant, here is a Planck constant. Here Planck constant will be treated to unit, but for physical sense, here, 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 here. Okay. And we have that this is a small displacement, but for small k and omega. But if k and omega are sufficiently large, these displacements can be very big. And if we have a classical system which can be modeled by this approach, then it is very interesting for theoreticians. But for practice, I don't know exactly. But theoretical aspects is very, very interesting for us. Thank you for attention. Have you any question about technique or about ideas for linear quantization and connecting with this topic?
Yeah. So the idea is to have experimental data and try to find that C parameter.
Yes. Yes.
So as far as I know, all current available data say in favor of tau equal to 1/2.
Yes. And somewhat more deeper, sigma 3, sigma 4. Sigma 1, 1/2. And sigma 2 is not interesting. Sigma 2, sigma 3. If we know sigma 3, we can suggest some quantization. Sigma 1 equals to 1/2. It's an arbitrary Hermitian quantization. It is not interesting. It is obviously. But sigma 3, Q tau, the third moment of symmetrization function. It is very necessary to examine in practice.
Can I ask you one more question? So we started with the linear quantizations. So in principle, is it possible to use the same technique or similar techniques to consider non-linear?
On nonlinear quantizations, they are more not complicated, but well, for example, linear and nonlinear. Q square pi square. Q p plus p q p q 1/2. Well, nonlinear. P times q square x minus 1 over q p x 1 over Q. Here we can construct an arbitrary function, and here only one arbitrary parameters, and this is an arbitrary function. It is not. It's very difficult to measure the function. We want to measure the value of parameter. So nonlinear quantizations practically not used. Well,
can I ask you one more final question? Or it's time to finish?
the main question: for what reason this is was written?
May I ask, and why non-linear quantization is not used in the practice?
Linear? Non-linear? We don't know what function we must use here. We don't know. Oh. For example, we don't know. And from these functions, the solutions of the evolution equations are depending dramatically. Well, thank you for attention.